Graphing harmonic motion, you need 3 colors once you have it all cut out and glued in. Let's get started. So the first thing we need to do is learn some basic vocabulary about graphing harmonic motion. However, we've already discussed most of this. We're just going to now apply it to graphs. So the first thing to do, pick your color for equilibrium position. If by chance it's the one you've used before, that's great. Equilibrium position. Highlight the word equilibrium position. Equilibrium position is the at-rest position of the motion. So when we are graphing a harmonic motion, this right here in the center, that is our equilibrium position. Go ahead and label that. Equilibrium position. Now let's talk about cycle. Cycle is one complete repetition of the motion, as we've discussed before. We are going to highlight one cycle of the motion. If you notice along the equilibrium position there, the x-axis, we have time is our measurement. So 0, 2, 4, 6, 8, 10, 12 seconds. We are going to start at time 0. Our graph starts here at the bottom. We're going to go past the equilibrium position all the way to the top, all the way back down to the bottom, and get back to where we started from. That is one cycle. Next word we're going to review is amplitude. Amplitude is the maximum distance of motion from the equilibrium position. So starting at the equilibrium position to the maximum right there, or starting at the equilibrium position to the maximum that direction, that is the amplitude. Now, 2 more words that are going to be helpful while we are describing this. All right? When we're looking at the very, very top of one of these waves, all right, this is described as a sine wave. When we're looking at the very, very top of that right there, there's a name for that very, very top point. That's called the crest. Similarly, we have a name for the very, very bottom. The lowest point is called the trough. T-R-O-U-G-H. Okay, that G-H makes an F sound. Trough. So crest and trough. Cycle, amplitude, and equilibrium position. Those are the key words I'm going to use again and again for us to describe harmonic motion and understand graphing it. Next, we are going to look at this right here. We are going to match up the movement of a pendulum to the graph. So start off with your color for equilibrium position. Now, picture didn't copy perfectly, but this is a pendulum. Where in this pendulum, the movement of that trajectory there, is the bob at the equilibrium position? D. Very good. Highlight that with your equilibrium color. Equilibrium. Because it's in the middle. So equilibrium means balance. This is the balance of the two extremes. Equilibrium position. Take another one of your colors. I don't care which. Let's go to one extreme. Let's look at the, I'm going to highlight the A. All right, that's going to be in another color. Go back to your equilibrium position color. Let's look at the graph. All right, everywhere we see a D, we're going to highlight it with the equilibrium position color. A, B, C, D. E, F, G, F, E, D. C, B, A, B, C, D. E, F, G, F, E, D. C, B, A, B, C, D. E, F, G, F, E, D. All right. If you carefully connect all of those together, does that look awfully familiar to the graph above? So now you understand why I call that the equilibrium position. Okay? Does that make sense?
Yes, ma'am.
Okay. Now let's look at one extreme over here. So A. A, B, C, D, E, F, G, F, E, D, C, B, A, B, C, D, E, F, G, F, E, C, D, C, B, A, B, C, D, E, F, G, F, E, D, D, B, A.
Let's have the crest.
Very good. So over here, right, crest. One extreme is going to be the crest. Now your other color. Then let's look at the other extreme. The G. So A, B, C, D, E, F, G, G, G. Okay? So, the trough. GH makes an F sound, trough. So, the other extreme gives us the trough. So, does that make sense? How the graph is made using the movement of a pendulum? All right. All right, now we're going to apply the same idea of graphing, but instead of a traditional pendulum, we are going to look at a spring pendulum. Okay? So if you see here in the gray, imagine I have a pendulum and I've spring pendulum and I stretched out and I let it go and it bounces up and then it stretches out and then it goes back up and then it stretches out. Okay? And as time passes, it creates the sine wave in the same shape, a sine wave there. Okay? So, start off with your color for equilibrium position. Equilibrium position is right here. That's the spring with the mass hanging on it, just hanging there, not moving. Okay? From there, you have to pull it to let it go. Once you've let it go, once you've let it go into cycling, it goes up. It comes back down right there. It's at the equilibrium position. Goes down to the trough, comes back up, equilibrium position. Goes up to the crest, comes back down to the equilibrium position. Okay? So, once again, this is our equilibrium position. Okay? Now, very important term here. The same color you had for amplitude, up above. Right there. Use that color. We're going to identify the amplitude here. The height of the crest and the depth of the trough, it's the same value. That is the amplitude. Okay? Now, key little thing here. We are measuring horizontally. Yes? No, he's not here.
He's not there?
Nope.
Okay, thank you.
You're going to cut that part back.
In this graph, time is on the horizontal axis. If you notice, we have one complete cycle here. We're starting at the crest, go through equilibrium, down to the trough, back through equilibrium, back to the crest. Back to where we started from, so the spring all scrunched up. When we do that, we have completed one cycle. So, your color for cycle. One complete cycle.
There.
Why didn't we start from the very beginning?
Yeah. Good question.
Oh, because it's just. No, no.
Because we're looking at from here to here.
And that's one cycle.
That's one cycle.
So that is
And the time it takes to accomplish that one cycle, that's the period. Okay? So, period measured in seconds. What's the F stand for?
Frequency.
Frequency. What are my units of measure for frequency?
Lowercase.
Hz, hertz.
Does it really hurt?
So, once you know using the graph what the period is, you can calculate the frequency using the formula. Now, on that same concept of frequency, let's back up to the original graph. So our very original graph, first graph here. What is the period, uppercase T? What is the period for this graph? Period is how much time it takes to do one cycle. So, we start at time 0 at the trough. We go all the way to the crest and return to the trough, and we have completed one cycle.
4 seconds.
The time to complete one cycle is our period, which is 4 seconds. Does that make sense?
Yes, ma'am.
Let's go.
Frequency. Frequency is the number of cycles that happen per second. All right? So if I look at this, in 1 second, from 0 to 1 second, I just have a piece of a graph. It's really hard by looking at this graph what that number is. It's like, what? So, the easy way to do it. Count the number of complete cycles you can see.
3.
So, 1 complete cycle, 2 complete cycle, 3 complete cycles. Do you guys see that?
Yes, ma'am.
Write down 3 cycles. Frequency is cycles per second. We did 3 cycles in how many seconds?
4. I mean,
In 11.
1,
12.
2, 3 cycles
12.
in 12 seconds. So 3 cycles divided by 12 seconds.
Schools.
125.
Okay. So,
Let's go.
3 cycles, 12 seconds, 0.25 hertz.
Hard.
Does that make sense?
Yes, ma'am.
Yes.
Okay.
Just a little bit.
Now, let's take the opportunity to do some practice problems on the OOPS page. We want to compare these 3 graphs. That's a little difficult the way they're drawn, so we are going to visually separate them using colors. So I'm going to start with my pink, and I'm going to start with that really short one, and I'm going to highlight 1 cycle. During the next section here, I'm going to highlight 1 cycle of the graph in the middle. And then in the last section from that point, I'm going to highlight the really tall graph with blue. And I'm going to highlight just 1 cycle. Now, we're going to compare and contrast these graphs. To do so, I'm going to start us off by identifying what is the same. The first thing that is the same is the equilibrium position. The line of symmetry for each of these graphs is all the same right there in the middle. The equilibrium position is the same for all 3 graphs. What else is the same? Well, let's start with a period. Look at the period. Is it same or different? Let's find out. So looking at the pink graph, at time 0, how many seconds does it take to finish 1 complete cycle?
8.
1, 2, 3, 4, 5, 6, 7. All right? Look at the green one. How many seconds does it take to complete 1 cycle? 1, 2, 3, 4, 5, 6, 7.
They're all 7.
They're the same.
Well, what about the blue one? Let's make sure.
I got you.
1, 2, 3, 4, 5, 6, 7. They all have the same period. 7 units, seconds. Now we are going to compare the frequency. To calculate the frequency for each of these graphs, we are going to use the formula cycles per second. So, actually, yeah, we'll do that. So, for the pink graph, okay, we have 3 cycles.
Ma'am, take 7 seconds.
All right. 3 cycles, sorry. 3 cycles divided by the time it takes to do those 3 cycles, which is 21 seconds. A very small number, 0.142857143. Okay? Significant figures, let's just simplify it, 0.14. And units are going to be what? Solving for frequency, units are hertz, HZ. When the pass comes back. All right, now let's do it for the green. Green graph. So 1 cycle, 2 cycles, 3 cycles. 3 cycles divided by 21 seconds. 3 cycles divided by 21 seconds, also 0.14 hertz. The blue graph, 1 cycle, 2 cycle, 3 cycle in 21 seconds. Hence, what do we know about the frequency of the 3 graphs?
They're the same.
Does not change.
Same frequency. Alright, so my question is this. What is different? Are these 3 graphs exactly the same? Are these 3 graphs, pink, green, and blue, exactly the same? Are they exactly the same? No. What is different? They have the same equilibrium position, same period, same frequency.
Guys, length.
Come on, use the vocabulary.
Amplitude.
Different amplitude. So let's measure those amplitudes. How would you measure the amplitude? A ruler. Simply put, the amplitude is, for my pink graph, 0.5 centimeters. The amplitude for the green graph is 1.3 centimeters. The amplitude for the blue graph is 2.1 centimeters. Pink, I'm going to first color the one that's most stretched. Once you have colored those 3 graphs, let's talk about equilibrium position. The equilibrium position for the 3 graphs, are they the same or are they different?
They're all different. Right now.
Equilibrium position is that horizontal point of symmetry. So if I look at the pink graph, the amplitude there, equilibrium position's right there. The green graph, amplitude right between the middle, same thing. The blue, crest and trough, middle of the line, right there. They all have the same equilibrium position.
Is it always going to be the same?
Yes. All right. Now I'm going to ask this. What else is the same? Look how tall those graphs are. The green one, the blue one, the pink one. Amplitude. They all have the same amplitude. And that amplitude is, from the equilibrium position to the crest, 1.3 centimeters. Period is the amount of time it takes to do one cycle. So let's look at the pink graph first. All right? 1 cycle, starting at the equilibrium position, hit the crest, past equilibrium, hit the trough, back to equilibrium. There's 1 cycle. How much time does it take? Well, if you go through, there's 5, 10, 15, 20, 21 seconds. It takes 21 seconds to do one other cycle for the pink graph. The green graph starts here, starts the equilibrium, crest, trough, back to equilibrium, and it takes 5, 6, 7 seconds to do that. So 7 seconds is the period for the green graph. And now the blue one. Equilibrium, crest, equilibrium, trough, back to equilibrium at 4 seconds. So 21 seconds, 7 seconds, and 4 seconds. Those are the periods for each graph. Are they the same or are they different?
Different.
Okay, they each have a different period. T equals 21, 7, and 4. All right, they each have a different period. What about their frequencies? Are their frequencies going to be the same or different? Okay, frequency is how many waves happen in a second, how many cycles happen in 1 second. So, how many cycles happen in 1 second? Is that going to be the same or different for each of these waves? It's going to be different. To calculate the frequency, we're going to use the formula 1 over T. Okay? So 1 divided by 21, you'll need a calculator to do that. Point 0.476.048. Okay? 0.048. What are my units going to be? Frequency measured in hertz.
Hertz.
1 divided by 7 for my green graph. .142. She's correct. 0.14 hertz.
Then is it okay if I added the 2?
That's okay. All right. 1 divided by 4. 0.25 hertz. That is the frequency for each one of those graphs. Now, with anything we've learned, the best way to really learn it is to practice. So now we'll go on to the practice worksheet.